Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating approach to 3D mesh generation. Building watertight meshes using spherical embedding. It's a really clever technique, and we'll unpack it step by step. Exciting stuff!
I'm eager to hear this. So the core problem is creating a seamless, error-free 3D mesh from a point cloud, right? Like from LiDAR data or something?
Exactly. We often get point clouds from various sources, and the challenge is connecting those points to form a continuous surface. Traditional methods like ball pivoting and Poisson surface reconstruction are great, but they sometimes leave gaps or self-intersections. That's where this spherical embedding method comes in.
Right, I see. So this new method uses a spherical projection. But a naive projection won't work because you can get overlapping points, right? That's where the unfolding comes in?
Precisely. A simple projection onto a sphere can lead to messy overlaps. The key is iteratively refining the point positions on the sphere using the Laplace-Beltrami operator. Think of it as a sophisticated unfolding process, gradually separating overlapping regions.
The Laplace-Beltrami operator. That sounds intense. Is it computationally expensive?
It's not trivial, no. The algorithm involves computing the nearest neighbors for each point, then iteratively adjusting their positions on the sphere based on the Laplacian. The author mentions that it's slower than Poisson reconstruction, but the trade-off is a guaranteed watertight mesh. A significant advantage.
So it's a trade-off between speed and guaranteed watertightness. Interesting. Does it always produce perfect results, though? Are there limitations?
Well, not perfectly perfect. The author points out some limitations. For instance, the choice of the initial center point for the projection is crucial, and, even with many iterations, some jaggedness or minor self-intersections might remain, especially in complex shapes. It's not a silver bullet, you know?
I see. So it's best suited for simpler, convex objects, then? Where the guarantee of a watertight mesh outweighs the computational cost.
Exactly. The article focuses on convenience store products, water bottles, candy bars, relatively simple shapes. For those, the guarantee of a watertight mesh is a huge benefit, even if it takes a bit longer to compute. It's all about the application.
And the author mentions using this for generating synthetic images for training machine learning models. That makes sense, needing accurate volumes and rotations.
Absolutely. Having a watertight mesh allows for accurate volume calculations and reliable transformations, which are essential for creating realistic synthetic data. Very important for AI training.
So overall, this spherical embedding method offers a compelling alternative to existing techniques, especially when a watertight mesh is paramount. But it's not a replacement for everything, right? It has its niche.
Precisely. It's a valuable tool in the 3D meshing toolbox, offering a different set of strengths and weaknesses. The author even suggests combining it with other methods for optimal results. A hybrid approach might be the best solution in many cases.
That's a really insightful point. Thanks for breaking down this complex topic so clearly. It's fascinating to see how different algorithms tackle the same problem with different trade-offs.
My pleasure. And remember, listeners, you can find the code and more details in the article linked in our show notes. Thanks for tuning in to Tech Bytes and News. Have a great day, everyone.
Bye-bye.